Right, here we go. We'll run through the 2019 Nat 5 paper. So question one's got the iron. It's an energy diagram. The input energy to an iron is of course electrical, and the output energy is heat. Okay. Now, the iron uses feedback to monitor the output. Right? If you have feedback, it is closed loop. It's measuring the output and it's feeding it back in. Okay, a lot of temperature sensors use closed loop to keep a control of the temperature. Maybe a street lamp, an automatic street lamp that automatically comes on in the dark, would be an open loop system because it doesn't measure the output. Okay, it's measuring the light in the sky. It's not measuring the light that's coming from the street lamp. Let's draw a symbol of thermistor. So a thermistor, it's a type of resistor. So we've got the resistor symbol, and then we've got the line going through it for the thermistor. Okay, so we're now talking about soldering iron. Calculate the power used. The power is the energy divided by the time. Okay, so the quicker you do it, the more powerful you are. Right? So the energy in this case is 6750 joules, and it's divided by the time. The time has to be in seconds. Okay, so there we go, 25 watts. Now, main air moves the cylinder, pilot air controls the valves. That's the difference. Yeah. So the velocity ratio, if you look in your data booklet, it's the speed of the input divided by the speed of the output. In this case, 800 divided by 320, 5 to 2, or in the decimal as well. Okay, right. So if this gear here is turning clockwise, this one will be turning anti-clockwise. Designing the connecting roads onto this thing, you'll be a civil engineer. Okay, it's kind of things to do with the ground is basically civil engineering. Monitoring the impact to local wildlife during construction, protecting the soils and everything. That'll be an environmental engineer. They'll be making sure that the environment is protected. Okay, there's big fines if you damage the environment. 2 positive social impacts. Right? I guess because you're going round about Aberdeen, you don't have to be in traffic jams going through it, so your journeys will be less stressful, your journey times will be quicker, there'll be less congestion in the city, the areas bypassed will be quieter and safer, there's less traffic flowing through Aberdeen itself, the city will be less polluted to live in, and there'll be jobs created. Right, A or not B and C. So here is the AND gate, so that's the AND C, and here's the OR gate, so it's a straight A or not B. So that's a NOT gate, the OR gate, and the AND gate. Right. Positive one with hydroelectricity. In use, it doesn't produce CO2. Reduce need to burn fossil fuels. It does not contribute towards global warming as much as a coal-fired station. Relatively pollution, clean in use. Okay, negative, the whole valley's been flooded. People might have been displaced out of the valley. There might be gas produced, methane produced in the valley that's been flooded. Okay, I mean noise when it's been built, I guess. Okay, right. So we have. There's the resistor arrangement. These two are in series, right? They have to be added together. So it's 1.2k, which is 1,200 ohms, plus that's 1,470 ohms, and that will be in series with the in parallel with 390. So here we have, this is one way of doing it, the product over the sum. So the 1470 is the 1.2 plus the 270. Okay, and it comes out at 310 ohms, the two significant figures. Right, the reading at ammeter 1 is 0.031 amps. So there's ammeter 1, so it's 0.031, and the resistance is 390, so that gives us 12 volts. So the voltage across there is 12 volts. Now, this circuit is in parallel, so across the 390 it's 12 volts, so across these two resistors it must also be 12 volts. Okay. Calculate the current A2. A2 is down the bottom. So again, as we're saying, it's 12 volts divided by the total resistance 1470, so that gives us 8.2 milliamps. And the third one, A3, well, A1 is flowing down here and going out that way, A2 is flowing up there, so A3 is just A1 plus A2. Okay, A1 flows there, A2 flows there, so A3 is A1 plus A2, and there we go. So the voltage across the 390, oh, I've done that. Right, and emerging technology. An awful lot of you did 5G. I gave you the marks for it. Driverless car might be a better one to do. Impact, maybe more fuel efficient, because if the computer's driving it, it won't be accelerating too harsh, etc. Okay, emerging technology one, I would go with the driverless car. It's easier to answer it with, and it's more emerging. Okay, I think the 5G probably has emerged. It has been sorted. Okay, this one, it asks for the system's boundary. Right, so that there is an input to the system. There is an output. All the rest is the system. The system's boundary goes round about everything that actually is the system. Okay. Now, then asks us to describe the whole system. The preset position is selected. It's fed into the control unit. The control unit, now the magic word is compares the actual position with the preset one, and it'll decide. It compares and it decides. The control unit compares and decides. It'll decide whether to switch on. Okay, so it'll switch on the output driver, which will drive the motor. The motor's position is measured by the position sensor, which is fed back to the control unit. Okay, and once the motor's reached the desired position, it'll stop. Okay, control unit compares these two, okay, and it'll decide what to do. A small current flows in the base, controlling a large current flowing from the collector to the emitter. Okay, so there's two outputs here. That's not A and not B. There you go, not A and not B. The dot is and. And there's another one here, which is A and B. And there's A and B, so it's not A and not B, or A and B. Okay, when you're doing this one, or this type of one, do it in columns. Right? So we've got letter G, so D and E are going to an AND gate, so we need D and D to give a 1 here. So the only times we've got D and D are there and there. These two are 1s, because that's the only time we've got D and D, the rest are 0s. That then gets inverted by H, so these are all 1s now, except for these two, which are 0s. Right? Now, Y, you have to have an H or you have an F. Right? So, anytime you've got an F, you'll have a 1. An F, you've got a 1. Now, anytime you have an H, you'll have a 1 as well. I think it lines up. There we go there. Okay, that one was well done. Just to be all there, everybody got it right. Right, the saw blade is going round and round. That's rotary. The piston goes back and forth. That is reciprocating. Okay. For the cylinder to in-stroke slowly, there needs to be a restrictor here, a unidirectional restrictor here. To outstroke, if it was outstroking slowly, it would be in this pipe here. Okay, so I'll do the full explanation of the circuit. Right, so if 1 is activated and 3 is this is the air bleed here. If 3 is activated, 1 and 3 have to be activated. The signal goes to 4, makes A go negative, activates 7. 6 and 5 cause a delay, goes back to 4, and that sends A positive. The one thing to remember is this signal here controls the closest pipe. So this one sends it positive. This one again controls the closest pipe. So this one sends it negative. Right. This question wasn't well done. Describe an advantage used in a microcontroller to control the movement of the piston. Right. So it's a microcontroller for this exact situation. It's not a general microcontroller advantage. Now, we've all done the delay thing. The delays aren't very accurate when you're just adjusting the unidirectional restrictor. Right. We could have a solenoid valve going at number 4 and using a microcontroller to control the solenoid. Then we could have a delay of days or seconds or milliseconds if we wanted. It would be very easy to control the delay using that. Now, this one wasn't very well done either. Now, the trick in doing it, if it's the in-stroke, right, the rod is getting in the way. The rod of the piston is getting in the way. So you've got to calculate the piston diameter and then subtract the rod diameter. Okay, so there we have the piston diameter. Okay, you can half the diameter if you wish and do it as 44 and pi r squared and 12 pi r squared. This one's doing it with the diameter formulas. And then you subtract the small one away from the big one, and that gives you an effective area of 5,600 millimeters. Calculate the force. Okay, so the force is the pressure times the area, so it's just 0.2 times 5,600. Okay, this one was well done. So we're taking moments about RB, so that's where we're spinning about. So the 930 is trying to spin it anti-clockwise, and the 930 is 3.6 meters away, and it's going anti-clockwise, so it's on the anti-clockwise moment side, and there it is. RA is trying to spin it clockwise, and it's 2.4 away. There we go, on the clockwise side, and the 680 is 0.4 away, and it's trying to spin it anti-clockwise. Okay, they've missed out a line of working there. I would write down what that is, and then get to that stage, and we'll wind up with 1508, 1.5 kilonewtons to 2 significant figures. Now, this one, if you do all the ups equals all the downs, if you round it to that answer, you get this answer. The ones that I marked at the start had the answer of 101 newtons. Later on, I discovered that the 101 is more correct than that 110, so I'm sorry about that, but I got there in the end. If you take moments about, what are we finding? That found RA. If you take moments about RA, you'll get RB. Right? If you do it that way, you get 101. Also, or 101.6, or 101.7 perhaps. If you use the 1508 and you didn't do the rounding here, again you'll get you'll get a better answer than doing it the other way. Okay, the SQ8 are wrong here. Okay, they've got the answer wrong. Right, the next one. State the term used to describe when forces acting on a structure are unbalanced. They are in equilibrium. Okay, if they're balanced, they're in equilibrium. That's the fancy term. Okay. calculate the cross-sectional area of support column A when a stress of 0.06 newtons per metre squared was measured for this force. So it's 2,500. So the stress is force over area. So substituting in, we've got 0.06 is 2,500 over A. The A is jumped diagonally, the 0.06 is jumped diagonally, and there we go, 42,000 millimetres squared. Okay. Visitor centres will be built next to the platform. Electrical engineer work is part of it. Now, these electrical engineers are not installing anything. They are the people who design them, the people who test them. Okay, they will not be using a screwdriver. Okay, so they'll design how to connect the visitor centre to the national grid. They'll calculate the power requirements of the centre. They'll select appropriate cables. Okay, the more power a cable has to carry, the thicker it'll be, and calculate the lighting requirements and plan the lighting layout. Okay, an electrical engineer. Okay, motorised winch. So data booklet, and we'll find the formula. Calculate electrical energy. EE equals I12 times T20 times V. Okay. There we go. So it's 220 kilojoules. If it's 64% efficient, that means out of 100 bits, you're only getting 64 out. Or if you like, 0.64 is the out over the in. So we know what the in is. So the out is 0.64 times the in. So it's 140 kilojoules. Most of you got that correct. Now, I don't like this question. Explain how the efficiency of the motorised winch could be increased. It's a standard answer. Lubricate the moving parts to reduce friction. Okay, friction causes losses due to sound and heat. This one, I meant to put in the dimensions of F. If you're doing it for real in the exam, you would measure F with your ruler, and then using the 5 millimeters equals 75 newtons, you would find that F turns out at 600 newtons. It's a scale question, that one. Tow cable's original length of 2.7 meters. Calculate the change in length of cable when the strain of 0.003 is experienced. Right. So the 2.7 meters, you can leave it in meters, you can change it to millimeters. This one has changed it to millimeters, and you've got 8.1. Okay, if you 2.7 times 0.03, you've got 8.1 times 10 to the negative 3, and that is equally correct if you put meters at the end of it. Two advantages using lamps in parallel. They'll all have the maximum brightness. If one lamp fails, the rest will stay on. Right. When the relay switch is off, there'll be a big voltage generated and it'll blow up the transistor. You need to have a diode across the relay to protect it. To protect the transistor. The transistor is the fragile component. That resistor is protecting the transistor. You could adjust this down to 0. Now put 5 volts onto the base, and that would damage the transistor as well. So as the light goes down, the resistance goes up, and the voltage goes up. State the effect on V in when the resistance of the variable resistor is decreased. So if that resistance goes down, this voltage here will be going down. So if that's going down, this one must be going up. Right. So there's two ways here. This is the way I've shown you. So if that's 2.7, that voltage there will be 2.3. If we know that 2.7, we know that's 1.6. I equals V over R. So we've got the current now. There we go. Where are we? This is it here. They haven't written as I equals V over R, but that's it there. That's the current. So we now know the current. then that's 2.3. R equals V 2.3 over I. There we go, 1.4K. Right. So the LDR has a resistance of 200 ohms. Now, this one, where I always start, there we go. So that is 1 kiloohm there. That one there, 1 kiloohm. So 200 must be less than that. That's 2 kiloohms, 3, 4, 5, 10 kiloohms, 30, 50, 70, 100 kiloohms. Right, so that was 1,000 ohms or 1 kiloohm. That line there is 2 kiloohms. So if we come along that line and then drop down, we come to that 7. Now, what does that 7 mean? Well, there's 1 lux, 2, 3, 4, 5, 10 lux, 30, 50, 100 lux, 300, 500. That line there is 700 lux. So the answer to that one is 700 lux. So advantage of using computer simulation: quicker to develop a solution, easier to change it, rather than building it. Reduces cost of designing, as if you make a mistake, you're not going to destroy a component. I guess it's safer. You can use very high voltages in a simulation, whereas if you're on the desk, it can get dangerous. You're not going to damage any actual components either. Economic impacts of using the harvester: it would be expensive to buy, maintain and run. Workers would lose their jobs, therefore lose their incomes. Harvester would be able to pick the fruit quicker, more fruit picked in a day, meaning more profit. Increased profit for the farmer, as wages would be reduced. Only ripe fruit would be picked, therefore reducing waste. No need to house so many workers, therefore increased profits. Workers would move away, causing local shops to lose income. Okay, calculate speed of gear D. Right, so we've got, there's the input speed. So that speed times that size must equal the speed of this one times that size. Okay, so 2,200 times 12 equals 48 times the output speed. Okay, there it is. There's the first line there. Rearrange that and you get an output speed of 550 revs per minute. So that one's doing 550 revs per minute. This one's on the same shaft, so it's doing 550 as well. Right, so 550 times 16 equals the output speed times 24. And we get 366.7. 370 revs per minute. Okay. Now this one, I let you off a little bit. It says in the question, use pin numbers somewhere. Include all pin numbers and delay units in your flowchart. Okay, so you should have seconds in, and you should have the pins in. Okay, so you're putting pin 7 on, pin 6 on, wait 0.8 seconds. All these were well done. Quite a few of you lost out on putting pin 7 off at the end, and I forgot to put that loop in myself, and I don't know if anybody added it either. Okay, there it is. This one wasn't so well done. It's pin 6, so it's just a line coming from pin 6 to the resistor, and then that's a symbol for a buzzer. That goes in at the end there. Right. And that's it. That's the whole paper covered. On the whole, so far, they've been well done. Thank you. And that's it.